All right, next up is day 14. Actually, if I recall, I was actually going to combine both of them, but I didn't. And then the apocalypse came. So, anyways, day 14. That is when we did a little bit of graphing. Rather, we drew the graphs out to kind of get some of your equations. But, well, let's commence. All right, so what a graph can tell us. It could tell us a few different things. It could tell us our final position. So here we have a position versus time graph. And we know that if we're to, let's say, have a trend line, the final position would be at A, and then your initial position would be at B, since the y-axis is your position. Your change in position is going to be C. Your D is your change in time. And then G is going to be your slope, which is your change in position, delta x over delta y, which directly relates to, sorry, delta x over delta t, which directly relates to, well, velocity. And so when we expand upon that, you were able to find out that I think we had delta x was equal to vi delta t plus, oopsie, I really should have put that over to the left more, but it didn't. You should have got, okay, so you got delta x is equal to vi delta t plus 1 half delta v delta t. We're going to pretend there's a t there. Okay, we're not going to pretend there's a t there. I'm going to write it again. Delta v delta t. Got it here. Basically, you did that by building up the graph, and I think you found the area right here, and then you added it up there. And basically, what that's trying to say is that these equations aren't magical. It's just filling in a graph, more or less. Same type of thing from the acceleration versus time graph. Sorry, velocity versus time graph. You can get acceleration from the slope because your acceleration is equal to your change in velocity over your change in time. And notice that this is your change in velocity, since velocity is on your y-axis, and this is your change in time, since it's on the x-axis. So the slope in the graph actually tells us something, and so that's kind of the big part that you should get from that. Guess I'll do a few practice problems. We have, it looks like an armadillo starting from rest, accelerates at 2.5 miles per hour per second for 10 seconds. First, we're going to find the acceleration in meters per second squared, and then how far the armadillo travels. So, I think I can write over here. No, I can't. No, here, I can write here. All right, so it's going to, we need to change 2.5 miles an hour per second. Okay, so 2.5 miles. Now, when it says miles per hour per second, it's saying miles over an hour times a second. Or it could be miles per hour per second, but that second is still going to be on the bottom here. And so then you got to decide, well, I've got to get this to meters per second. Okay, well, I know that for every mile there are 1,609 meters. And so that right there would give me meters per hour second. Well, that's the problem. We don't need meters per hour second. We need meters per second squared. I know that for every 1 hour there is 3,600 seconds. So I put the hour on top. That leaves me with seconds squared on the bottom and meters up top. And then I grab my calculator to do some calculating. And I get, looks like 1.1 we're going to go with. So equals 1.1 meters per second squared, or meters per second. How far did the armadillo travel? Well, as I said in the last lecture, delta x is equal to vi delta t plus 1/2 of a delta t squared is, delta t squared is probably my favorite equation. We're going to use that. So delta x, notice that the armadillo started from rest, so its delta x is equal to 0 plus 1/2 of the acceleration of 1.1 meters a second squared, and then your time squared, which is 10 seconds. So, at this point, we could do some calculations. 10 squared is 100. Multiply that by 1.1 should give us what, 110. And then divide that by 2 and we get 55 meters. Probably unrealistic for an armadillo, but artistic liberties. We'll go with that. Artistic liberties. 55 meters. Actually, no, I think an armadillo could probably pull that off. They are kind of fast sometimes. Alright, so 55 meters. Alright, moving on. I keep putting up this meme. I'm not sure how much longer you guys are going to understand this, but if you see Napoleon Dynamite, you'd get it. It's probably my favorite part of Napoleon Dynamite, to be honest. Especially when he takes that stake and throws and hits that guy in the face. He hits Napoleon in the face. Oh, that was great. That was classic. Classic. Anyways, quarterback is running down the field at a constant 7.5 yards per second and has 30 yards until he scores. A linebacker runs after the quarterback at 8.5 yards per second, but is 2 yards behind the quarterback. Does the linebacker catch the quarterback, and if so, how far and when did the linebacker catch the quarterback? So, alright, we've got a quarterback's running down the field, 7.5 yards per second, 30 yards until he scores, so we know he's on, what, a 30-yard line. His formula is going to be delta X, and I'll call it Q for now, for the quarterback, is equal to 7.5, and I'm not going to convert this one, because it's not going to make a difference in this case. 7.5 yards times time. The linebacker is delta XL. He is faster, so he's 8.5 yards per second times delta T. Now you may notice, hey, we've done this before, but not recently. Yeah, this is more of a review problem. I threw this in a long time ago. It made a lot more sense when we were in class and going at a regular time, but it may seem a little disjointed now, but I figured it's not going to hurt you. Anywho, excuse me. Notice I said XQ and XL. The problem, the reason that I have that here is that we see that the linebacker is 2 yards behind the quarterback initially. So if the linebacker is to catch the quarterback, that means that he's going to have 2 yards less of running, so that delta XL should be whatever the quarterback does, delta XQ. Wow, that is not a delta XQ. Delta XQ minus 2 yards. That's the only way it can happen, right? Okay, so then I'll make that substitution. I'll take this whole brouhaha, and I'm going to put it into this brouhaha, and then that gives me, okay, and I'll put it in parentheses and say, hey, I made a substitution. It's delta XQ minus 2 yards, and I'm probably going to run out of room, so I probably shouldn't have done it this way. And that's equal to 7.5, and I'm just going to put delta T because I'm just about out of room here. Let me make it a little bit better. Let's try to make it a little bit smaller. Minus 2 yards equals 7.5 yards per second delta T. Close enough. All right. Well, we still have 2 unknown variables. We have delta T and we have delta XQ. But I do know that delta XQ is equal to 7.5 yards per second. So, well, let's utilize that. We have 7, oops, it didn't look too good. We have 7.5 yards per second. Delta T. And I made a boo-boo back here, you probably noticed. It's supposed to be 8.5 yards per second. Why did I put 7? I guess I was struggling to get that in here. Sorry about that. So we have 7.5 yards per second. That's in for times delta T. That's in for delta XQ minus your 2 yards, and that's going to equal 8.5 yards per second delta T. Print C. Okay, so Moving that to the other side is going to give me a negative 2 yards is equal to a negative 1 yard. That's really a bad yard, by the way. Yard per second, delta t. Negative, negative, we want to be positive. Pete's, yards will cancel, and your time is going to be 2 seconds. So it's going to take the linebacker 2 seconds to catch the quarterback. Well, that answers the does the linebacker catch the quarterback? Well, we know eventually they are going to. But we want to know how far, when. Well, we got the when, but how far? Well, we know that the quarterback was 7.5 yards per second. So I could just take my 7.5 yards for every second times 2 seconds is going to be equal to 15 yards. And so he started on the 30-yard line. He went 15 yards, so he's going to end up at the 15-yard line where he gets tackled and is sad because he didn't get very far. So, yeah. So basically put on the test, which if you've read my announcement, is going to be take home. You will have one question where there might be a time differential. Basically, the quarterback or the linebacker in this case starts 5 seconds behind, or somebody starts a distance behind. Like, okay, in this case, the linebacker was 2 yards behind. But you'll have something along those lines, and you'll need to set up 2 equations, and then you'll need to make substitutions. So it'll be very similar to this problem. So, all right, if you have any questions, please email me, and that is it for this lecture.